Welcome to video 4.7 in our first Principles of Astrophotography series. In this video, we discuss the physical origins of the forbidden oxygen-3 and sulfur-II emission lines, which are targeted by narrowband filters.
Why, if they're forbidden, why are we talking about them?
The short answer is that these lines are forbidden by a particular approximation called the electron dipole approximation in calculating a very difficult quantum mechanical problem. But they're allowed by higher order if you do a better job of approximating the problem.
No, I see why they're forbidden. My brain is forbidding me from understanding this. This video is based on section 4.7 of our first Principles of Astrophotography book, which is linked in the description below. I'm Ren Edwards.
And I'm Boyd Edwards.
Let's talk sensibility.
So this is a slide that we showed in a previous video of the Ring Nebula. We talked about the hydrogen alpha, beta, and gamma lines, and in this video we're going to focus on the oxygen and sulfur lines. Also, there's a nitrogen line that overlaps with the hydrogen line as well. So that's the focus of this video. So a little bit of chemistry or physics, whichever you want to think about it as. Oxygen, neutral oxygen, that it comes in its normal configuration, has 8 electrons, 8 protons, and 8 neutrons. So if you're in an energetic situation, which these nebulae are, you've got ultraviolet photons, and we'll talk about this in a future video, ultraviolet photons that kick electrons off of the atoms. And singly ionized oxygen, an oxygen atom from which you've extracted, kicked off 1 electron, has, instead of 8 electrons, 7 electrons. But the 8 protons and 8 neutrons are still hanging out in the nucleus. They're totally fine, not affected by this. And doubly ionized oxygen is the ionization state that we really are interested in, because it's the one that produces those 2 visible lines. So doubly ionized means you've stripped 2 electrons of the 8, leaving 6 electrons in the atom. Now, from your introductory chemistry, you may remember, some of us may and some of us may not, that there are different ways that electrons can spend their time in an atom. They're called subshells or orbitals. The 1s orbital, you can have a maximum of 2 electrons in the 1s orbital. This is spherically symmetric, and so what this orange circle is intended to denote is where that electron likes to spend, is it a he or a her? Their time, should we be politically correct?
Yes, yeah. Good idea.
Okay, so where that electron wants to spend their time, and it's equally likely to spend its time anywhere over the interior of that sphere. That's the 1s shell. Then the next, and this 1 refers to the n equals 1 that we did in the hydrogen. Remember the principal quantum number where we had an energy that's minus 13.6 eV divided by n squared? That's the very same n. It's a principal quantum number.
Okay.
So here's n equals 2. The reason that things are a little more complicated here is that hydrogen is simple because there's only 1 electron. But when you get, for example, 6 electrons, like in oxygen, they interact with each other. They're all negative. They repel each other. And so that makes things much more complicated. Negative things don't like to be next to each other. They like to be far apart. And so when you have an electron in one subshell or orbital that overlaps with another, it'll change the energy of that subshell. So the 2s orbital or subshell has, the electron can spend its time in the center or near the outside. Now this orange is intended to denote positive parity or a positive wave function, and the blue is intended to denote negative parity or a negative wave function. And what does that actually mean? The square of the wave function in quantum mechanics gives the probability of finding that electron. So this one's still spherically symmetric. It has a positive wave function in the middle and a negative on the outside, but it can spend its time anywhere inside this sphere. Then the p
Is the
orbital,
positive part inside of the whole negative part? Or is it beside?
Yeah, so the positive part would be inside here, and the negative part would be outside. So it's like a baseball that's the center of a beach ball, or whatever. Yeah, but it's all spherically symmetric. Then these p orbitals, 2px, 2py, and 2pz, you can put at most 2 electrons in the 1s subshell. You can put at most 2 electrons in the 2s subshell. And then you can put at most 2 electrons in the 2px, and 2 in the 2py, and 2 in the 2pz. Now these are not symmetric. So you've got a positive on this side and a negative on this side. And that just means, so that's the parity of the wave function. The electron will spend its time either here or here. Well, it's a cloud. It's moving between those two sides equally, but the two sides are distinguished from each other by the phase or the sign of the wave function. Now, you might be saying, this is because, but I think a famous physicist once said that nobody really understands quantum mechanics. You just get used to it. And so get over it.
I can't.
You can't get over it?
My brain forbids it.
So, but the px, py, and pz, this one's oriented along the x, y, and then this is oriented along the z-axis in the 3 coordinate directions. You get these orbitals. Now the interesting thing about doubly ionized oxygen, it has 6 electrons. 2 are going to go on this 1s shell. That's this one right here. 2 are going to go on the 2s shell because they're the lowest energy shells. And then you've got 2 electrons that you're going to spread out somewhere between the 6 p subshells. So you could put 2 in the 2px and 2 in the 2py and 2 in the 2pz, or you can put one of the electrons in the 2px and 1 in the 2pz, etc. So any combination, those electrons have a lot of different ways of occupying those orbitals.
So these states they coincide at the same time. 1s,
Yes.
2s, and
Yes.
the
Yes.
3,
No, I think
2p.
I understand your question. That's a great question. So suppose we have 1 electron in the 2px orbital and then 1 electron in the 2py.
Right.
Then that electron is just, he's hanging out. They are hanging out in this subshell, and this other electron is hanging out in this shell like that. And but the interesting thing is that there's a whole number, if you do all the combinatorics and figure out all the different possibilities of where you can put these 2 electrons amongst the 6 2p shells, then you get 5 different states that, 5 different energy levels that can result from that. And I'm not
So
going to say any more
the
about
states are a result of which electrons are in which
That's right.
p thing.
That's right. That's right. And so that, and we'll talk in the next slide, I think it is, about there'll be 5 different energy levels based on where those electrons are spending their time. And it's transitions between those levels that create the oxygen-3 emission line.
Okay. Well,
So principle 61.
that's orbital parity. And just so you know, the s and p orbitals are respectively called even and odd orbitals.
So what does that mean? Here's the s and here's the p. The s are spherically symmetric. So that's another way of thinking about even. And thinking about spherically symmetric, it can be anywhere inside this sphere. But the p orbitals are odd, meaning the wave function is negative on this side and positive on this side. And this comes into play in an important way in trying to identify these emission lines.
And the S's are coaxial, right?
Coaxial, yeah, usually the word coaxial, in my experience, is used to describe something with cylindrical symmetry rather than spherical symmetry. But it would be the cylindrical analog of spherical. So coaxial usually is a cable with a central core and then an outside part that comes up.
And the center is in the center. It's not
Right.
on the
Right,
side.
exactly. And I should also say,
They're on the same axis, but on the X, Y, and Z axis.
right, but you're talking about the s orbitals here, right?
Right,
Yeah.
yes, yeah.
And so those really, the best way to think about it is just to extend that coaxial argument into
Into a sphere.
into a basketball. So you have a basketball and a baseball that's inside of it.
But the
And,
baseball is always in the center.
yes, and that's the important thing. The nucleus, where the protons and the neutrons reside, is right there at the center, and the electron is orbiting around in a symmetric way. Same thing here. The protons and the neutrons are right at the center of there, and this 2py subshell describes how the electron spends its time around the nucleus.
Okay.
Okay, even and odd.
I don't get it, but I get it.
Yeah, nobody understands quantum mechanics. Energy levels.
Principle 62, energy levels. Energy levels of various arrangements of electrons in a partially filled subshell are denoted by term symbols of the form 2s plus 1lj.
Okay, so we do go into considerably more detail in our book describing these term symbols. But these are the 5 energy levels that I was referring to earlier. Depending on how you put those 2 electrons in the unfilled 2p subshell, gives you 5 different energy levels, with 3p0 being the lowest energy level and 1s0 being the highest energy level. And I should say that these energy levels are very low-lying excited states of these atoms. You're not promoting, for example, one of these 2s electrons. This is a closed subshell. You're not taking one of those and putting it into the 2p. A lot of transitions are done that way. And all the transitions in hydrogen that we talked about involve changes in the principal quantum number. Here we're not talking about that. All these electrons, these 2 electrons in the 2p subshells, all of them have n equals 2.
In the odd subshells.
In the odd subshells, all of them have n equals 2. But it's just the different amounts of overlap between the wave functions that determine the slight differences in these energies.
Principle 63, oxygen 3 lines. Transitions between energy levels of the 2 electrons in the partially filled 2p subshell of doubly ionized oxygen produce 2 blue-green oxygen 3 emission lines.
So this is just summarizing what we've been talking about. We got 2 electrons in a partially filled 2p subshell, and they produce 2 blue-green lines. And those are these bad boys right here, or bad girls.
Thems.
Bad thems. This one's the stronger of the 2 lines. It's located at 500.7 in standard air.
Uh-huh.
And then the one that's a little bit weaker is generally not targeted by oxygen 3 filters. It's at a wavelength of 495.9 nanometers. And these are the actual transitions that produce the 2. So the one that really matters here is the 1d2, that's this one right here, to the 3p2. So it's a transition between those 2 energy levels. And that transition, just like the transitions in the hydrogen atom, going from 3 to 2 or 4 to 2 or 5 to 2, these produce these particular emission lines. Now, these brackets here are denote that it's a forbidden transition. So in spectroscopic notation, if a line is forbidden, and we're going to say a little bit more about what we mean by forbidden. And I should also say that this is not an area that I've worked in a lot in physics. My expertise is in theoretical nonlinear dynamics and other things other than this. So I spent a fair amount of time trying to understand this problem over last summer. And I was inspired by a Cloudy Nights post by Jack Gansley. And he's referenced in our book. Jack raised the question, where do the sulfur and oxygen lines come from that we're targeting with our narrowband filters? And there was a discussion, and there was a post by a fellow named Frank Suits. I'm not sure if I'm pronouncing this right, but Frank and I have corresponded, and Jack and I have corresponded as well. And Frank recommended a particular book by a fellow named Osterbrock, and that's also referenced in our book, where I learned over painstaking time in the summer trying to understand these lines. And it was interesting when I corresponded with Jack just a few weeks ago. He said, oh, I thought you were referring to the write-up I did about that. He said, after I posted that on Cloudy Nights and raised the question, and there were a few comments, but not really a real resolution of the problem, he said, I wrote up a complete write-up, and it was earlier this year, actually. So he sent me a copy of that, and that's also referenced in the book. It's an excellent description, and it mirrors pretty much exactly what we're talking about here. So thanks to Jack and Frank
Nice job, Jack.
For that interaction, and Jack for getting me thinking about this. I've been wondering about the same thing too. I want to understand where these lines come from. I don't feel satisfied just saying, well, there's a 500.7 nanometer line. I want to know where it comes from.
That's good enough for me.
Is it good enough for you? Just another 500.7? Yeah. Okay. So these are those two lines. There's the 500.7 forbidden oxygen-3 line, and here's the 495.9 nanometer also forbidden oxygen-3 line. We'll say a little bit more about why they're forbidden in just a second. Okay, we talked about nitrogen. So there usually astrophotographers don't buy a nitrogen-2 filter, but there is a line that if your hydrogen alpha filter isn't too narrow band like ours, or 2.5 nanometer, they're too narrow to capture this nitrogen line. But if you have 5 nanometer or 8 nanometer, you're going to capture some of this nitrogen line. And I want to talk about that too. The nice thing about it is there's hardly any new physics, because it's basically the same as the sulfur lines, as the oxygen lines, sorry. Okay, so here's nitrogen. So back to your high school chemistry. Nitrogen has an atomic number of 7. That means it has 7 electrons, 7 protons, 7 neutrons. And if you singly ionize it, you're going to strip one of those electrons off, so that takes 7 electrons down to 6. Well, that happens to coincide with the exact number of electrons in the oxygen-3, the doubly ionized oxygen. We were dealing with 6 electrons. So there's 2 in the 1s shell, 2 in the 2s shell, and 2 spread out between these two 2p subshells. So the physics is basically the same. The only difference is that there are fewer protons and neutrons to hold those electrons in than there were for the oxygen. So we get exactly the same energy levels as we did before, and we get 2 transitions. So remember, for oxygen-3, we had the 1d2 to 3p1. We also get a 1d2 to 3p1 in nitrogen. 1d2 to 3p1. And we get a 1d2 to 3p2, 1d2 to 3p2, this transition right here. And so those are the 2 nitrogen lines, one of which comes really close. This one here is a 658.3 nanometer line. That's this bad boy right here for nitrogen. Any questions about nitrogen? Yeah. Okay, great. All right, so the only one left is sulfur. And sulfur, as we saw in some of the spectra that we showed in the last video, sulfur is not important in the Orion Nebula, and it's not very important in the Ring Nebula. So in regular emission nebulae, planetary nebulae, sulfur doesn't play much of a role. But it does play a role in the Crab Nebula, and you might remember that was a sharp line in sulfur. And so if you're shooting the Crab Nebula, you definitely want to shoot some, if you have a sulfur filter, shoot some sulfur. But honestly, with the Orion Nebula, don't worry about sulfur. Don't even shoot it. Sulfur is a more complicated atom. It has 16 electrons, 16 protons, 16 neutrons, and I'll try and go through this pretty quickly here because it's essentially more of the same. Singly ionized sulfur, and I should say, I haven't mentioned this yet, but you use the chemical symbol S, which denotes sulfur, and if you put a Roman numeral 1 after it, for one reason or another, in spectroscopy and in astronomy, S1 means neutral
It's
sulfur.
the first state of nothing.
It's the first state. It's just got an equal number of electrons and protons, so it's completely neutral. The negative electrons balance out the positive protons, etc. When you put a 2 after it, that means singly ionized. The way these electrons are configured in singly ionized sulfur is there's 2 in the 2s subshell, 2 in the 2s, 2 in the 1s, 2 in the 2s, 6 in the 2p subshell. So this subshell, instead of what we saw with oxygen and nitrogen, this is now filled. It's a filled shell. And a filled shell doesn't carry any angular momentum. Then you get 2 in the 3s, and then 3 in the 3p subshell. So you're going to take 3 electrons and decide where to put them amongst all those 6
So
possibilities.
that's the exciting one.
This is an exciting one because you can put 1 here, and 1 here,
That's cool.
or you can put 1 in this one, 1 in this one, and 1 in that one. These two, the arrows in each case mean spin up or spin down electrons. Electrons come in 2 varieties that way. Again, it's quantum mechanics. There are, again, 5, but not the same 5 energy levels that we saw with oxygen and nitrogen. And these are odd because there are 3 electrons in the partially filled shell, which is an odd number. That's why, if you want to know why that O is there, before we had 2 electrons in the 2p subshells, and that's even because there's only 2.
Got it. Yeah, that's good.
Yeah. All right, you want to read that one?
Oh, sure. Principle 65. Sulfur-II lines. Transitions between energy levels of the 3 electrons in the partially filled 3p subshell of singly ionized sulfur produce 2 red sulfur-II emission lines.
Perfect. Are they forbidden or not?
Yeah.
Because there's a bracket around them.
Ah.
Yeah, they're forbidden, and we'll talk about that in just a second.
Everything
So
today is
here-
forbidden. It was a good guess.
Yeah, so here are those 2 lines. They're very close to each other. So 671.6 plus 1.5. So these only differ by 1.5 nanometers. So they're really, really close to each other. And that's why, well, here you can, it just looks like one little blob
They're
here.
close to each other, but further out.
Further out from when?
From the center?
Oh, you mean the, because we're up in the 3p levels? Yes, that's exactly right. So these guys are even further out from, because this is the principal quantum number n equals 3. So they're further out from the nucleus. Okay, and the 2 transitions are 2d05 halves to 4s03 halves. So there's that transition. And then there's 2,303 halves to 4s03 halves. So those are the two. Yeah, okay. Yeah, wake up, Ren. Everything's going to be fine. But now you know that this is the essential physics right here. These are transitions between the partially filled subshells that create these emission lines.
All right, principle 66. If the number of electrons in odd orbitals is even or odd, the term parity is, in odd orbitals is even odd, the term parity is even odd.
Okay, so if the number of electrons in odd orbitals is even, then the term parity is even. So that's what we were talking about before. With oxygen and nitrogen, we have 2 in these odd orbitals. And because that number is even, the parity, it's called the term parity, is even.
Is even, okay.
And because the number here in these 3 P's is odd, it's called the term parity. It's not the term parity, it's called the term parity. I don't know if that makes any sense at all. Okay, so that's why we have these odd markings here for those. But here, I would like for you to notice here that this is a transition between an even term and another even term. This is a transition between an odd term and another odd term. Now we get to say what forbidden means. And this I sweat bullets trying to figure out what all this meant. And so you're getting the benefit of my bullets sweating.
Giant brain.
I don't know about that.
Principle 67. Forbidden transitions. Transitions between terms of the same parity are forbidden by the electric dipole interaction, but are allowed by the magnetic dipole and electric quadrupole interactions. These transitions have low transition probabilities and are difficult to observe in terrestrial experiments, but are observable in low-density emission nebula.
Okay, so what forbidden means is that you have this difficult quantum mechanical integral that you have to calculate to predict these transitions. The simplest approximation you can make in calculating those transitions is called the electric dipole interaction. Do these both have the same parity? Yes, they're both even. So that's forbidden. That's the reason why they're forbidden. It's a transition between two terms of the same parity. And the same thing here. These are forbidden for that too. So a higher order approximation of this difficult quantum mechanical integral is called the magnetic dipole, and another one called the electric quadrupole. Both of those interactions allow transitions between terms of the same parity. And so they save your life. Those just thank goodness tonight for the magnetic dipole interaction, because otherwise you wouldn't understand the sulfur transitions. All right, transition probability.
All right, principle 68, transition probability. The transition probability is the reciprocal of the mean lifetime of that transition.
Okay. So one more thing about this one. These guys are difficult to observe in terrestrial experiments. We'll say more about that in just a second. But are observable in low-density emission nebulae. The transition probability is the reciprocal of the mean lifetime of that transition. These transitions that occur between different energy levels in an atom, they're random, spontaneous events. You cannot predict, for example, for the hydrogen alpha line, when that electron is going to hop between level 3 and level 2. It's impossible. There are certain things you just can't know. It's a random, spontaneous event. It's a radiative transition, and it has to sit there in level 3 until it decides it wants to transition down. You can't tell it when to go. And the transition probability, so if you think about the mean lifetime, so how long that electron sits in level 3 before it transitions to level 2, you can't predict for any particular one, but you can say, well, let me do this experiment 1,000 times and find the average amount of time that it spends in level 3. That's called the mean lifetime. And 1 over the mean lifetime is called the transition probability, or sometimes called the transition rate. So if the lifetime is very long, if it's going to sit there in level 3 for a long time, then that mean lifetime is long, and you take 1 over a big thing and you get a small thing. So the transition probability is very low. It has a low probability of transitioning down. These forbidden transitions have very long mean lifetimes and very low transition probabilities. And so what happens on Earth is that the densities of gases on Earth are much, much higher than the densities of the gases in space, of emission nebulae. So the problem with the forbidden transitions here on Earth, and why they are not generally observed unless you really go out and want to see them on Earth, the problem is that there's so many collisions between these atoms, or between these ions, that before that electron that's in the higher state can transition randomly down to the lower state, it gets kicked by another atom. There's a collision with another atom, and it disrupts the process. And so you don't get that transition happening. So let me just demonstrate what the differences are between densities on Earth and densities in emission nebulae. This is a square that shows 10 dots plotted at random inside that square. And if you imagine squishing that square down to a cubic centimeter, so make it into a cube. So we're just looking through a cube and seeing 10 atoms that are inside that cubic centimeter, about the size of a... do people use sugar cubes anymore? I mean,
Sure.
they're a little hunk of sugar that's about that size. It's about that size.
Horses like them.
So some emission nebulae have densities of 10 particles per cubic centimeter. So it would look like this. They're that dense. I mean, that not dense. Other emission nebulae have number densities of 100 particles per cubic centimeter. Others have 1,000 particles per cubic centimeter, and that might look like a lot. But let me explain. This is the high end of densities that you can see in emission nebulae. 10,000 particles per cubic centimeter. An ultra-high vacuum on Earth, the highest practical vacuum you can achieve on Earth is 100,000 particles per cubic centimeter. And also 1,000,000 particles per cubic centimeter, that's 1,000,000 particles per cubic centimeter. Yeah. And that's ultra-high vacuum in the best laboratories on the Earth. You say, well, wait a minute. When I look through air, it doesn't look black and opaque like this. And the reason is, remember, these atoms are really, really small.
I'm just looking between them.
You're just looking right through that million, even in ultra-high vacuum, it's perfectly transparent because they're so small. That's how many there are in air. The air in this room, there are 25,000,000,000,000,000,000,000,000,000,000,000 particles per cubic centimeter.
See some open spots in there.
Yeah, it's just flecks of dust on my computer screen.
Right.
So that's what air is like. And if you want to work it into, Ren likes to think about it in billions of billions. So it's going to be 25 billion, something like that. Anyway, it's huge number. And you just have to think about the fact that you're walking around in this air there's 25 bazillion particles that are banging against your eyes all the time at about half half a mile per second is about how fast they're going. They're banging into your eyes all the time. So,
Ouch.
but anyway, the point here is that here on Earth, even in the best vacuums on Earth, by vacuum I just mean it's you've taken as many air molecules as you can out of the deal. They're much denser than the emission nebulae that we're looking at. And a lot of times we think about these emission nebulae as being opaque, but they're not. They're transparent. Most of them are. We're enhancing the color as much as we possibly can to get as much color as we can. But generally, if you just look at them, not with a long-term exposure, they're just going to look transparent. Yeah. Thanks so much for watching.
And we'll see you next time.